Hello and welcome back to Paleocast. My name's Dave Marshall and today we are joined by our very own Elsa Panciroli. Hello,
Hi.
Elsa.
Hello, how are you?
I'm alright. I am in a hotel room in Stavanger in Norway.
Oh. Wow.
Yes.
That sounds fun. Is it fun?
No, I'm in quarantine for working on the oil rigs, so I can't actually leave my room. And I've been in Norway for, it's been about a month and a half now, and I might be away for another 2 months.
Is the minibar empty?
The minibar was empty, yes. But I get 3 meals a day delivered to my room. Three-course meals. It's ridiculous. It's the most amount of food that anyone has ever tried to feed me.
It doesn't sound too bad.
It swings and roundabouts. Yeah. You know, it's gives and takes.
How much longer are you going to be stuck there?
I don't know. Honestly, like, when I'm working on the rigs, which is a legitimate job for a paleontologist doing biostratigraphy for the oil industry, your schedule just goes out the window. I'm just at the mercy of an oil company who have me here, just sitting, waiting to work, not knowing what I'm doing day to day, which makes it incredibly difficult to arrange and sort out interviews, especially when you don't bring any audio equipment, which fortunately I have done this trip. So that's why you've not had any interviews, people. So I'm very sorry about that. But you've been busy as well, haven't you, Elsa?
I have. Well, yeah, I have been busy. I mean, like everybody, it's kind of difficult getting things back on track after this last year, which has been so crazy, hasn't it?
And we've got a global pandemic going on as well. Forgot about that for a second.
Not quite finished with that yet. It seems to be lingering a little bit longer than I think we all hoped for. But the last month has been quite good, and things are picking up. And I have a book out, so that was quite exciting.
And so that is what we'll be talking about today. Well, around the book. So I think it's a really momentous occasion for any researcher to publish a book. I mean, this is your first... Is it your first one?
It is, yeah.
God, that must have been exciting and daunting.
Yeah, and kind of surprising. I'm not quite sure how this happened, but I'm delighted, obviously. I think most researchers, I should say for anybody who doesn't know, this book is called Beasts Before Us, and it's telling the sort of untold story of mammal origins and evolution. And I'll come back to the untold bit in a second. But it is a popular science book, so it's written for a wide audience. There is science in there, and there's some referencing, but I could try to keep it light. But what I wanted to do more than anything else was make it so that really anybody can read this story, because I think sometimes as scientists, we get so caught up in the details, it can be hard to then talk to normal people. So I hope that both scientists and so-called normal people will be able to read this.
So whilst I think it would be nice to sit here and work through the book chapter by chapter, I think we can have a nice kind of parallel discussion here that covers many of the same topics as the book, but in places we'll add more details, and in other places referring to the book would be obviously the best thing to do, because we're only going to be talking about 45 minutes or something. So I'm sure the book goes into a lot more detail.
Yeah, I mean, so for those who know me, I mean, my speciality as a scientist is early mammals, but by that I mean the ones mainly sort of in the Jurassic, a little in the Cretaceous, and a little bit into the late Triassic, but around about basically the time of dinosaurs, right? So that's the bit that I kind of personally know about. So writing a book like this, which is, as I say, it's the untold story. So it's the bits you don't generally get to hear about. So most of us know about the last sort of 66 million years since the dinosaurs became extinct. And then some of us also know about what I was just talking about, the mammals in the time of dinosaurs. But very few people then know further back than that. So into the Permian, or even further into the Carboniferous, basically the whole lineage, Synapsida, right from the beginning. So it was quite challenging to write it for me, because obviously, those are not all my areas of specialism. I had to find out and research an awful lot of stuff, which was so much fun, but hard, but really good fun. Yeah.
Yeah. So before we get into those details, let's have a bit of context about who you are and how you got into paleontology. So when did your interest first develop?
Well, I guess as a paleontologist, you're meant to say, I've always wanted to be one since I was 2 years old or whatever. And that's not really true for me. I did go through that phase of loving dinosaurs, and everyone always loves fossils. But I kind of went off that again, more into other subjects, human origins, but then really more art and literature and things. And it was much later. Yeah, it was much later. I actually went to university as a mature student, kind of realizing that actually science was kind of cool. Quite enjoyed it. And I did environmental science, which is not, of course, quite paleo. But in one of the classes, we did this lecture on climate change. And one of the papers that our lecturer got us to look at was on climate change in, I think it was actually the Permian, and specifically ocean circulation in the Pacific in the Permian. And I could not believe that we could actually know that stuff. Like, that's just amazing. And it still amazes me. I find that mind-boggling. And that sort of realization that these things that were really ancient were much, for me, much more interesting than the stuff that's happening right now. I guess I love ancient stuff. So I switched and took a sidestep and ended up doing the master's at Bristol in paleobiology, and then a PhD. And then here I am. I'm now a researcher at the University of Oxford Museum of Natural History. So that's kind of my journey, really.
So what would you do if you weren't a paleontologist? Do you think you would have pursued that literary route?
Maybe. I've always wanted to write. Oh yeah. I mean, I was telling somebody this the other day when I was in secondary school, about 11, 12 years old, right at the start of secondary school. My history teacher said that I wrote the longest essay they'd ever had from an 11-year-old in their entire career. Like, I have always loved to write. I think I have learned brevity since then. But yeah, I think maybe you're right. Maybe I would have ended up writing no matter what I did. I like telling people about stuff, sharing those kinds of wow feelings that you get from finding out about science. And I mean, you obviously feel it too. That's why you do Paleocast, isn't
it? Yeah. How much of an influence did growing up in Scotland shape what you did and what your research interests are?
Well, yeah. I mean, I guess it's funny. Yeah. I mean, now Scotland does play quite a large role in my research because I study a lot of fossils from there. But to be honest, I grew up in this really rural part of Scotland, very small village. And I had absolutely no idea that there were really important fossils in Scotland at that time. And I certainly didn't really know anything about the rocks. I was incredibly interested, but there was nobody locally who knew anything about that kind of stuff. And of course, we didn't have a library. This was before the internet, so you couldn't look things up so easily. There was a traveling library that would drive around in a van. And I remember asking the person who ran it to get me a book on geology and fossils. And when it arrived, I remember it was just filled with this arcane language that I totally couldn't understand or make head or tail of. So yeah, really, to be honest, Scotland's geology didn't have, as a science, that much of an influence simply because I couldn't access that information. But later, and actually, weirdly, when I had left Scotland and gone to study in Bristol was when I first started to realise that Scotland not only has fossils, but has incredibly important ones for lots of different groups and lots of different time periods in history. So since then, it's become, a particular fascination for me. And I think all of us are always sort of kind of taken by the fossils from our own countries, aren't we? Because they mean something special to you, don't they? So yeah, it definitely influences me now.
Okay, and where do your research interests lie? You've said before about the Mesozoic mammals, but what about them specifically? Like, what kinds of methods do you use? What kinds of hypotheses are you looking to answer with your research?
Well, at the moment, my fellowship is actually looking at growth and development in early mammals. And we use a lot of CT data and synchrotron data. And it's a really, there's a lot of different questions that we're kind of trying to tackle. And I've only just started. Plus, of course, with COVID, it's a bit delayed as to how far I've gotten. But we're sort of essentially looking at the teeth and the bones and signs of how quickly they grew and the different stages in their ontogeny that they reach. So, for example, when do they get their milk teeth? How rapidly do they become adults? Is it very slow, like you would see perhaps in reptiles, slow throughout their lives? Or do they have a more modern mammal sort of pattern? Are they growing up really quickly, reaching adult size and then staying the same size? And these are questions that are very difficult to answer, of course, because we have so few fossils. And also because, how do you look for the kind of signs of things like that, except in the actual incremental growth patterns in the bones and teeth themselves? So that's what I'm actually interested in right now, and at the very sort of early stages of data gathering and learning all about the subject.
So today we're going to be talking about your book. You've already given us a brief introduction to it, but could you really tell us why you wanted to write it?
Oh, yeah. Why did I end up doing it? That's a really good question. As if I didn't have enough to do when I was doing my PhD at the same time. I think it kind of ended up happening naturally because I was writing for The Guardian, doing science outreach sort of stuff, about different evolutionary topics. So I started accumulating little short pieces I'd written about particular subjects. But simultaneously, of course, as a student, I was finding out a lot about the background of my own research. And it seemed amazing to me that there's really this whole part of the mammal evolutionary story that a lot of us don't really know anything about, or maybe a lot of scientists do know something about it, but a lot of regular folk know nothing about this. Most people have this picture of us really only, our mammal heritage only beginning when the dinosaurs, the non-bird dinosaurs, disappear. And to suddenly discover that not only did it extend back to the time of dinosaurs, but you can draw that line even further back, right the way to the very fundamental split between the first animals that came out onto land, between the line that we would call sort of the reptile line, the sauropsids, and the mammal line, which is Synapsida. Of course, mammals are just one of the many members of that group. And discovering that split was so ancient, I mean, this is like 360 million years ago, was actually quite shocking to me. I didn't know that before I became a student. And I wanted to sort of basically share that surprise and that wonder with other people, because I thought to myself, if I didn't know that, then loads of other people don't know it either, and they'll probably be as interested as I am, I hope. That's really the reason I ended up writing it. It was a combination of wanting to tell that story, but also already beginning to tell it through some of my other work. So the two kind of were plonked together and turned into this book.
So what style is the book in? So is it like an academic textbook? Is it an overview of the history of research in the field? Or is it a combination of all of your experiences, or just everything, all of the above?
Well, it's definitely not an academic textbook. So, if that's what you're expecting, this is not the one for you. This is really more narrative. It's supposed to be more for a wider audience, So I try to tell stories about the different animals rather than getting too bogged down in technicalities. Now, that's not to say that there isn't a lot of science in there. I've stuck to the science and I've kept it accurate, and I've covered the things that needed to be covered and explained. But I've also tried to not overwhelm people with sorts of detail that really, is only for specialists. In order to do that, I also have sort of brought in certain figures in the history of the subject and how they came to to do what they did and how they came to make the discoveries they made. Particularly Sophia Kielen Javarovska, who's a sort of heroine of mine. She's a mammal paleontologist who she led the Polish-Mongolian expeditions to the Gobi Desert to discover not just mammals, but also dinosaurs and other fossils. So it's a mixture of all different things, a bit of history, a bit of science, a bit of, also I talk about decolonization and things like that, and try to put book basically in a sort of more modern context. And also avoid, I think a lot of paleontology books, they end up in order, people expect them to be written by an Indiana Jones sort of personality who talks a lot about themselves and what they do. And although I do bring in my own fieldwork and experiences to it, it's really not about that. It's about the animals, it's about evolution itself, and it's about the other people who have studied this subject and who've made these amazing discoveries. And of course, how technology is changing what we can find out from fossils.
Okay. Well, I like a lot of those technical details, and I think our audience might do as well. So let's jump into some some of the basics of what mammals are and where they came from. So fundamentally, what is a mammal and which anatomical characters define them?
So I'm going to take that as meaning like a bona fide mammal rather than the bigger group, Synapsida. Okay, so of course, if you ask someone what makes a mammal, they're usually going to say they produce milk for their young. They usually say that they give birth to live young, although of course platypuses and echidnas don't. They still lay eggs. They tend to have a body covering of fur, and they tend to have an elevated metabolism, endothermic, although that can vary a great deal. There's some that are warmer blooded than others. And of course, those things are all true, but you can't obviously tell whether an animal in the fossil record has a lot of those traits because they're all soft tissue traits, aren't they? So what we need to do, of course, is look at a combination of genetics and fossils to try and figure out at what point those different traits emerged. But we also then look at characters in the skeleton, which I'm sure the listeners of Paleocast will be really familiar with that. Different traits in the skeleton and in the teeth that kind of signal when an animal is beginning to change and helps us tell one family from another. So with a combination of all those things, we can kind of say that mammals originate around about 200 to 160 million years ago. The earliest members based on their skeletons there's mammalia forms and then there's mammalians. So the earliest members are like Morganucodon, which you might have heard of. It's this small shrew-like creature from Wales. And what makes something a mammal is there's a lot of characteristics, but the real main one is its jaw joint, which sounds so incredibly arbitrary, but mammals famously have just one bone in their jaw, the dentary, as opposed to other groups which have multiple bones making up their jaw. And they have very specialized teeth. And a lot of what we talk about when we're studying mammals is all about the teeth and the chewing and what they ate and how they ate it. So in mammals, they only have this one single jaw joint, which forms between the dentary and squamosal, as opposed to between sort of any of the other bones being involved. Although caveat here, there are some on the in the sort of boundary between mammals and not quite mammals that very annoyingly keep two jaw joints just to confuse matters, because biology is always like that, isn't it? There's always got to be some exceptions. But that's kind of the most fundamental split, really, between something that is not quite a mammal and something that is a mammal, is that jaw joint. And then after that, you begin to get lots, of course, of other different groups, mammalians, therians, all the rest of it. And each one of those has its own suite of different characters. But that's really the kind of most important thing.
Okay, so you mentioned today we've got the placental mammals, of which we are one. We've also got the monotremes, which are the platypuses, and the
platypuses,
echidna.
You're right.
Platypuses.
Yeah.
And the echidna. And then there's another one, isn't there?
Marsupials. Yeah,
Ah, yes.
placentals, marsupials, that's right. Yeah, so kangaroos and koalas and possums.
So just looking at the modern then and getting the breadth of mammals that we have today, what are the main differences between them? And do those differences tell us anything about their evolution?
Mm. Well, there's quite a lot of differences. I mean, picking out some of the main important ones. I mean, obviously, we'll start with the easiest one, which is the monotremes. So that's platypuses and echidna. They are, most people would consider them to be weird. In some ways, they're weird. In some ways, that's a bit of a sort of legacy judgment thing. We think they're weird because obviously we're looking at it from generally from a Western scientific perspective. That, you know, I think if science as we know it had originated in Australia, we'd probably think monotremes are pretty normal. But anyway, putting that aside, they are actually slightly odd because, I mean, the platypus has this so-called beak, although it isn't actually a beak. It's soft and rubbery, and it's filled with these incredible electroreceptors that allow it to detect movement and of its prey underwater. And it's got this very strange, rigid pectoral girdle around the shoulders and chest. So it moves kind of funny. It is actually an odd animal among all mammals. So the two of them, echidnas and platypuses, they are the only ones left of this branch of the mammal tree, which we know from genetics split at least a sort of 160 million years ago, perhaps longer than that. And they used to have lots and lots of members in their lineage. Particularly, we find some of their fossils in South America, for example. Probably they're in Antarctica, probably under the ice sheets there, and of course now in Australia. But we have just the two left now. So that's them, and they still lay eggs, but they do produce milk, but they don't produce it from like a nipple. They have a sort of patch of skin that the milk oozes out of, and the young lap it up. So they're quite different in a lot of different ways. And there's other differences in the way their chromosomes are arranged and so on. Then looking at kangaroos and other marsupials, they famously, of course, have a pouch that they keep their young in. And the form that takes also varies a bit. But they are giving birth to live young. But the young are born incredibly underdeveloped. And they actually sort of crawl, they pull themselves from the womb to attach to a teat inside the pouch, and they finish off their development there. So they're being born extremely young. Early in their ontogeny, I should sort of say, early in their development. And then placentals, on the other hand, again, live birth, but they retain the young for a lot longer. So the young of placental mammals tend to be born a little bit less helpless, although that varies a great deal as well. So those are sort of three of the main differences. People do tend to focus on those as the sort of fundamental differences between the three groups, although obviously there's all kinds of other anatomical peculiarities, things like their ankle bones and so on. But yeah, that's broadly speaking what the three groups are like today and how they're defined.
And so what I was getting at by asking if that tells us anything about their evolution, just looking at the modern ones, does the fact that monotremes lay eggs give us clues as to how mammals might have evolved and what they evolved from?
Yeah, sorry, I actually forgot the second part of your question there. You're quite right. So the platypus and echidna, they're basically retaining the original trait of laying eggs that all mammals would have shared. And we're pretty sure that basically synapsids probably right back to the beginning, or certainly right back to the beginning, were egg layers. At what point when I say at what point they stopped doing it, I should actually, of course, add a caveat. They might have repeatedly in different lineages stopped laying eggs and had live young. I mean, looking at reptiles.
Whoa.
Yeah, it's definitely, I mean, it's almost definitely happened more than once. We just don't know because we don't have the evidence for it. But looking, for example, at reptiles today, I think there's as many as, is it like 24 different independent instances of reptiles giving birth to live young. Now, if it happens so often in different groups of reptiles, it's almost certainly happened multiple times in synapsids as well. But the fossil evidence for this, we just don't have it yet. They probably would have, they would have had almost certainly soft eggs, more like you see from like a turtle, for example, today, that very soft shell. And those things just don't preserve. And particularly for when mammals become generally quite small during the time of dinosaurs, if the ones that were still laying eggs, those eggs would have been so tiny. They really would have been, a platypus egg is about the size of a marble or a grape, let's say. So it's really quite small. And platypuses are relatively large. They're maybe as long as your forearm. So if you imagine a tiny little mammal like Morganucodon, the one I mentioned earlier, which is so small it could just stand on your hand. It's really like a little mouse-sized thing. If it was laying eggs, those eggs would have had to have been so tiny that finding them, I'm not saying we can't do it, but it's going to be hard. It's going to be hard to find that evidence. That would be the holy grail, though. If we could find evidence of what point different mammal groups stopped laying eggs, that would be really, really interesting. But at the moment, there's not the evidence. There's also not really evidence in their skeletons that's conclusive for whether they laid eggs or had pouches either. It just doesn't show up because these are soft tissue traits.
It sounds like hard work being a mammal researcher.
I should add, obviously there is evidence for all these sorts of things in genes. So there's been studies kind of looking at the different genes in, of course, the platypus has been a really key animal for this because it diverged from the rest of mammals so early on. And we can trace back at what point in the rest of the mammal groups, we can look approximately at when they started to lose some of the genes associated with egg production and started to gain some of the genes that they have for milk production, which of course is what they focused on because of the differences in how they bring up their young. But even then, it's what these molecular divergence times and everything are like. They're really broad, and it's the same spectrum I said earlier. It's somewhere around about 160, maybe as early as 100, right back to as old as 200 million years ago. That's a huge span of time. We just don't know.
Okay, so in your book, you look at the earliest origins of what I guess we could call the mammal lineage, but when we look at every organism alive on the planet today, every single one has direct ancestry back to that origin of life. So where do you cut it off? At what point do you say, I'm going to write my book on mammals from this point downwards?
Yeah, I do actually say in the book at one point that I could have just gone right back to Luca, last universal common ancestor, and try to tell it from there. But I chose to briefly outline the origin of tetrapods, just because I thought it was really important. One of the things I really wanted to tackle in the book is that we still use some terminology that really needs to get thrown in the bin, right? And one of the biggest ones of those for me is the term mammal-like reptile. I think it's an incredibly unhelpful term. It's a kind of legacy of a time when we did think that mammals evolved from reptiles. So I chose my starting point in the book to tackle that. So I had to go right back to that fundamental split between the lineage that includes mammals, the synapsids, and the lineage that includes reptiles. So that took me back to a sort of round about 360 million years ago when we first have the first tetrapods and then the first amniotes. So that's why I chose that point to start the book. And it's a lot further back, I think, than a lot of people tend to go when they talk about mammals. Hence why I say this is like the untold story. It's the bit you don't usually hear about.
So both the reptiles, the diapsids, and the mammal lineage, the synapsids, evolved from a tetrapod that was neither.
Absolutely. Yeah. And that's really important because I talk about this in the book too, that really it's because we look back in time, we look back and say that something looks like a thing that exists now. So we look back at these early tetrapods and say they look very lizard-like or reptile-like. But actually, it would kind of be more accurate to say that a lot of lizards look very early tetrapodomorph-like, because, of course, these early, as they call them, tetrapodomorphs and tetrapods, they were neither. They weren't reptiles. They weren't mammals. They were their own thing at that particular point. And you're right. one of our common ancestor with reptiles is one of those creatures, which was neither a reptile nor a mammal.
Okay. And so you said that we first see this split between the two in the Carboniferous period. Is that right?
Yeah, that's right.
That's a long time ago.
Yeah, I know. As I say, yeah, a lot further than people think. And we have all of these amazing sort of cousins that basically, kind of people talk about the time of dinosaurs and that they, air quotes, ruled the world. So I guess if you want to apply that same language in the Carboniferous and the Permian, it's really our lineage, the synapsids, that kind of did that. They were incredibly numerous. They were huge. I mean, some of these creatures, things like Dimetrodon early in the Carboniferous and then later in the Permian, animals like Asteminosuchus, they grew to like 3 meters in length. Absolutely enormous animals. And even this early on, they're starting to show signs of the things that we now associate with the mammal lineage. Things like there's evidence that they may have had slightly elevated body temperatures, some of them. Possibly towards the end of the Permian, they might have had some kind of hair or whiskers. That's a bit controversial. We don't know for sure. And certainly their teeth. So mammal paleontology is all about teeth. Their teeth had already started to become specialized. We already start to see the first saber teeth, the first, proper canines, and the first, what at this point we just call post canines. But of course, later we would then refer to them as molars and premolars in later lineages. This is already happening over 252 million years ago, even though we tend to associate it with creatures from really the last 100 million years. So yeah, we have a very old vintage.
Wow, so in that Carboniferous Permian heyday of the synapsids, are the fossils just abundant? Are they everywhere? Are they really easy to study? Complete, beautiful, pristine specimens?
It's like all groups, some are and some aren't. So there are particularly great places to study them. I should separate out the earlier sort of Carboniferous ones, what were generally called Pelicasaurs, although actually that's not a monophyletic term, so it's kind of a little bit outdated. But that's things like Dimetrodon, Edaphosaurus, these ones that they were previously called mammal-like reptiles, but of course are not reptiles at all. They have the big sails on their back, quite sprawl-legged, with a long tail, with the ones, of course, that are meat eaters have quite intimidating big mouths full of teeth and quite pointed canines. I should differentiate them, which come earlier, from the slightly later therapsids. They were even more diverse. Big plant eaters, quite small, sort of digging creatures. Some what they would call hyperpredators as well. So depending on which group it is you want to look at, you have to look at different parts of the world. So in the book, I talk about how some of the earliest of these so-called Pelicasaurs, like Dimetrodon, were found in North America, particularly in Texas. And they had been found previously by indigenous people, and then later were also studied by the likes of Cope, as in Cope and Marsh, Bone Wars. And this is part of the reason that this is one of the synapsids that's quite well known, is that it was discovered quite early on. There's some really complete skeletons, gorgeous looking things. There's some photos of them in the book. And they're quite eye-catching and dynamic. And I think this is one of the reasons that Dimetrodon in particular is one of the synapsids people know about, is because it just looks amazing, right? And then I talk a little bit later on in the Permian about these therapsids. There's a lot of them found in South Africa and also in Russia. But yeah, as for where you, of course, find fossils in general, it's the same as for all groups. There are always certain parts of the world where the rock layers just happen to be preserved better. And I've just mentioned some of them there. But that doesn't mean that we won't be finding them elsewhere in the future as we explore other parts of the world.
Yeah, it's a really important point, that, and it leads on to whether or not you think that the picture of synapsids in the Paleozoic is complete. For instance, you say that they originated in the Carboniferous. Do you think that could get pushed back even further with a lot more study? Do you think that we've pretty much got it?
That's a difficult one for me to answer. I mean, I think I was saying earlier on, this is kind of not my area of specialties, so I will answer, but I should caveat that it's not. This is not an expert answer. This is just based on discussions I've had with people who really do know this stuff. People like Christian Kammerer, who's like proper expert in this, yeah. Anyway, from the sense I get from them is that we're probably relatively accurate. But I mean, the thing is, any group that you're looking for fossils from, you are, of course, only getting one data point, and that's only a minimum estimate, isn't it? So I guess theoretically there might be something slightly older, but it's unlikely because you're kind of constrained by then the tetrapod fossils that come before that. So you're unlikely, for example, to find an early synapsid when you're only really just getting the first tetrapods on land. So it gives you a constraint. So if we do find that the time wiggles back and forward a little bit, I don't think it's going to wiggle by much. Certainly looking at the Carboniferous, I would say almost certainly as our origin.
Sure. And so then rounding off the Paleozoic, it ends with the colossal mass extinction between the Permian and then the Triassic in the Mesozoic era. It's an era, isn't it?
I'm always really bad at remembering which ones. Yeah.
Insights into the mind of a paleontologist.
It's funny because I quite often think I do know the answer, but I don't want to say yes or no in case I'm wrong.
This is why I always keep the International Chronostratigraphic Chart on my desktop. The Mesozoic era.
It's on my wall.
I was correct. You can download it from www.stratigraphy.org, and it's very useful. Anyway, yes, so we had that colossal mass extinction. How did the synapsids fare throughout that? Because like 95% of marine species, or what was it, went extinct. It was huge.
Yeah, in trying to write about this, I did. It's difficult to get, and of course, it's like all these extinction events. There's lots of estimates, but certainly a minimum, it seems, of at least like 3/4 of life died. I mean, this is the biggest mass extinction event of all time. I don't think there's even a bigger one. No, that is the biggest one, isn't it? So yet. Well, yeah, very important caveat there. How did synapsids fare? Well, we were just talking about how in the Permian in particular, we've really got this therapsid heyday where you have these incredible mega herbivores, these hyper carnivores. You've even actually got some early climbing therapsids as well. So some of the first climbers, of course, lots of diggers as well. So, I mean, it's really quite ecologically diverse. So obviously, as you would expect, this Permian mass extinction, it pretty much, is like a guillotine for an awful lot of these groups. But famously, in the very earliest Triassic, it is actually a member of the therapsids that does really well, and that's Lystrasaurus. So this thing looks like, it's a Dicynodont. It looks kind of like it's got the face almost of a turtle, but with saber teeth. Its body is built like a little pig. So this is a very, very strange creature. So if you imagine a pig with a turtle's head and saber teeth, then you're right on the money. I mean, this is a bizarre little animal. But it was a plant eater. There was several different types of Lystrosaurus, but they basically were incredibly prolific. And I mean, I can't remember what the statistic was, but it's something like 1 in every 5 animals alive in terrestrial environments was Lystrasaurus. It was just so numerous. But it was a disaster taxa. In other words, it did really, really well in the immediate aftermath, possibly because although a lot of plants were, of course, destroyed in the devastation of the mass extinction event, which was caused by volcanism in Siberia, massive volcanism, which led to climate change and which led to acid rain. Although a lot of the trees disappeared, there would have been a lot of herbaceous plants growing, so sort of low-growing, I don't know if herbaceous is the right word, I'm sure a paleobotanist will correct me, but basically low-growing, leafy sort of plants. And these seem to have been perfect for Lystrosaurus. So it did really well in that aftermath. And we've got a few other things made it through, particularly cynodonts. And so, of course, we are cynodonts. These are some of our closest relatives and ancestors that made it through as well. So mostly quite small-bodied. Superficially, I guess you might say they're kind of dog-like, with slightly splayed. We've still got slightly splayed out stance, rather than the legs directly under the body, although not as much as in earlier groups. So a few of those made it through, but a paltry number of the incredible diversity that was in the Permian. So it was, there was some survivors, but in this sort of aftermath, although Lystrasaurus did really, really well in the short term, in the longer term, as we all know, of course, it was the reptiles that were kind of first off the mark to start growing in body size and taking over different ecological niches and basically becoming this sort of incredibly diverse crocodile line and dinosaur line animals that we know and perhaps love. Maybe, I don't know, maybe not everybody loves them.
I don't.
No, I don't think you did. That's why I said that. I have to say, I do love dinosaurs. I in my book, I'm constantly being a bit negative about them, but I do actually love them. I just love mammals more.
So how did the synapsids fare with the rise of the dinosaurs and the crocodilomorphs? Were they marginalized, outcompeted?
So this is, of course, one of the things I'm particularly interested in is, first of all, the science of what you've just asked, but also the perception of mammals in the time of dinosaurs is one of the things that really turned me onto this whole subject. So the traditional picture, of course, is that as we have this rise in the different lineages of reptile, that the mammals are sort of relegated to the darkness and that they basically become nothing but sort of terrified snack food, just scuttling underfoot, and that they're all, small and a bit boring, basically. And I think that perception is really understandable when you look at the fossils that we had up until really the 1970s of mammals in that time period. They were all, there was very few fossils at all. All the fossils that we had were just a few teeth and jaws, maybe the occasional bit of skeleton, but they were all very small and kind of samey. They looked just like little shrews. So it was really understandable that that was our perception. And this began to change in the 1970s and has rapidly morphed entirely since then, as we've sort of realized not only were there a lot more of these mammals than we thought, but that they also weren't all small. We've started to find much larger body size. By larger, I mean still constrained. So the biggest mammals in the time of dinosaurs are animals like Repenomamus, which was in the Cretaceous. It's known from Asia. And it was sort of the size of a hefty badger. And it was found a hefty badger, and it was found with one of the specimens of Repenomamus was found with dinosaur babies in its stomach. So this of course is again rewriting this picture. Okay, dinosaurs obviously ate mammals because they would have eaten anything smaller than themselves if they were meat eaters. But mammals were eating baby dinosaurs because anything eats anything, it's not just a one-way relationship. So here we have a mammal eating dinosaurs in the Cretaceous. It's kind of cool. So that's the sort of first thing, is body size. We begin to realize there's a lot more variation than we thought. But then we've also begun to discover really ecologically diverse mammals, and from quite early on as well. So the group that I'm particularly interested in and specialize in are called Docoduntins. And they are a very early branching member of mammalia forms, not mammalians. So I said earlier, there's like a slight difference in that. It's just a technical difference. And so they actually have this incredible ecological diversity. We've now, since I think the first one was found in 2006, and since then there've been multiple others that are, for example, specialist swimmers. One of them's like a kind of otter-like animal, quite big as well, about 800 grams. Yeah, and it was preserved with webbed feet as well. So we know that it's got webbed paddly feet. And it was also preserved with fur outline around the body. So we know it had a thickened wide tail, which of course would have been perfect for helping paddle it through the water. We also have this incredible specialist digger, essentially a Jurassic Mole. called Docofossor, which was very heavily specialized for subterranean life. And we know that from its paws. My supervisor, Zheshi Luo from a PhD, he told me about how he was one of the people who studied it. And he said when he first looked down the microscope and saw its front paw, he just couldn't believe what he was seeing, because it's basically got a little mole shovel paw. And you can actually see how some of the digits, like in a modern mole, and moles belong to several different, the word mole, I should quickly caveat, isn't just one type of mole. There's lots of different types, but they all have the same kind of body plan, which involves this shovel paw. And they often have reduced digits in their, reduced numbers of segments in their fingers, and sometimes actually have lost some of their digits or kind of fused them together to make shovel paws. And Docofossor had this, and it had it in the Jurassic. So, well over 100 million years before the earliest moles that we see in the modern mammal lineages. So it's quite an extraordinary find, because we can also look at how the hand has been changed and relate that to changes in genetics. So we know which genes were triggered in Docofossor to change its hands to be that shape. Wow. So this kind of stuff, this kind of stuff is essentially revolutionized the study of mammals in the time of dinosaurs. We also have gliding mammals, we have climbing mammals. I suspect, although some people will argue with me, but I suspect that probably in the time of dinosaurs, mammals were just about as ecologically diverse as animals of the same body size are in modern environments, mammals of the same body size. So small mammals today.
I did not know about these. I mean, I'm a paleontologist. I'm not a vertebrate paleontologist, but still, I do a lot, and I've never heard of these animals. I hadn't conceived that there would be that much diversity and ecological diversity. Like, I know that I probably fit into the category of misconceptions that made you write this book. I just assumed there were little shrewy things.
Yeah, and that's what made me start to write the book. And then, of course, it ballooned out into this much bigger story, because most people don't know about this stuff. It's relatively new. But I mean, I think the other reason we don't get to hear about it is because of the time period they lived in. I mean, the moment that you mention it's the time of dinosaurs, particularly if you're talking to the media, it gets totally and utterly overshadowed. The actual subtlety of the story, the sort of interest in these animals, it gets overshadowed by reptiles. And it's understandable. I mean, they're very exciting. But, when we start trying to understand the bigger picture of how evolution works, it's really important to get this subtlety. And, it kind of casts aside our assumptions about where we come from, I think.
Right. Audience, in the comments, let us know if you have heard of Jurassic Mole and Jurassic Otter and Jurassic Flying Squirrel. I want to know. I want to know if it's just me.
Yeah, I would actually be really interested to hear from people, how many people had heard about that.
Yeah.
And the other thing I think is important to talk about with mammals from that time period is also, you mentioned there about the competition, competition with dinosaurs. Again, the kind of traditional idea was that mammals remained small because dinosaurs were not only predating them, but potentially competing with them. And this never really sat well with me and with certain other, researchers, but it's very difficult to test a hypothesis like that, because when we look at the pattern, it seems to be at the mass extinction event at the end of the Cretaceous, the non-bird dinosaurs become extinct, and of course then we have modern mammals. So it looks like an open and shut case. But actually, I was really lucky to get to work with one of my colleagues, Neil Brocklehurst, and Roger Benson and Gemma Benevento recently, and we looked at the skeletal traits in mammals in the time of dinosaurs and directly afterwards, trying to understand whether this competition idea was actually true and try and test it. And this is really interesting because we actually found that it's partly true and partly totally wrong. So in the time of dinosaurs, mammals, as in our sort of lineages, so the Therian mammals that include marsupials and placental mammals, they do seem to have been, I guess you would say, constrained, held down. They don't diversify into a lot of forms. And all this diversity I was just talking to you about was actually found in the other groups of mammals, the ones that lived alongside them. They're all also mammals, but they're not the ones that include our ancestors. They're basically cousins, brothers and sisters, but not direct sort of ancestors. So it looks like, in fact, it was competition between our ancestors, the Therians, and these other groups. It was that competition that prevented our lineage, the Therians, from doing a lot of interesting things. But these other mammals, they were going crazy. I mean, they were, as you say, flying squirrels, turning into moles. So there's a little bit of grain of truth in that story, but it's not the whole picture.
Yeah, I think it's interesting as well in the context of the competition with dinosaurs, that you don't see dinosaur moles or dinosaur otters or dinosaur flying squirrels, winky face.
Yeah, well, they talk about make out like being small is a bad thing, but actually it's a really brilliant evolutionary innovation. Being little is a great idea. Lots and lots of other animals are doing it too. And even today, among mammals, 80% of mammals are what we consider small-bodied, certainly under like 5 kilograms, but most of them much smaller than that, under sort of 500, 300 grams even. Because it's a really, really great body plan. It's a really great way of life, being small and being generalist as well is really useful. So yeah, we shouldn't look at their smallness in the time of dinosaurs as a bad thing. It's just a different innovation. It's like becoming a microchip instead of becoming, I don't know, what's really big? Humvee. Oh, I was going to say Humvee.
Yeah, and think of things like food. You don't have to eat as much. You don't have to spend as long finding food. If you find a berry, you could eat that and be done for the day.
Yeah, well, but bear in mind, being warm-blooded does mean that you have to eat more to keep those sort of fires burning. But it could also have contributed to why they did better than some other groups during the mass extinction event at the end of the Cretaceous. And of course, of the dinosaurs, the birds also did well, and they are also, have elevated body temperatures. So, and of course, care for their young as well, many of them. So these things are probably not coincidences. It probably contributed to their survival.
Right. Well, before we kill off the non-avian dinosaurs, let's first see if we have any crown group mammals in the Mesozoic. And by crown group, that would be all of the ones that are alive today, represented by ones that are alive today, and they're not relatives. How would you...
I know what you're trying to ask, Ken. I get you. So the three groups that we mentioned earlier, monotremes, marsupials, and placental mammals, yes, we have got our earliest origins in the time of dinosaurs. The monotremes split off much, much earlier than the other two, so right back to at least 160 million years ago in the Jurassic. As for the Therians, so that includes placental mammals and marsupials, we don't know exactly when they split, but certainly by the early Cretaceous, they had split into two quite distinct lineages. So yeah, I mean, basically we can sort of trace ourselves back to that point. And these animals, the ones that we know about that belong in these lineages are animals like Eomaya, which is potentially a very, very early, I want to say placental line mammal, because it's not actually a placental mammal as such. And then on the other side, there's Cyanodonts, which belongs to the line that then later includes marsupials. And they look, well, without sort of denigrating them, they just kind of look like little tree possums. I mean, sort of quite undistinct creatures. We can tell them apart usually by their teeth and by the sort of details of things like their ankle bones.
Okay, so the end Cretaceous mass extinctions just happened. Sorry about that. Was it all party hats and cake from there for the mammals?
Probably not. So there's differing opinions about whether this sort of some of the crown groups of mammals, whether they appeared just before or just after the mass extinction event. I think it's similar for birds. There's a lot of sort of controversy there, so I'm not going to come down either way on that. But let's just say, right, mass extinction has occurred, the earliest mammals of these groups, they quite quickly became larger, but there were still a few of these other types of mammals I mentioned earlier, these sort of cousins and related groups that are no longer alive today. Some of them persisted as well. So there was a bit of competition with them to begin with. And this sort of early Paleogene is just a mess, to be honest with you. I mean, speaking to researchers who specialize in the mammals from that time period, I mean, most of them, they're kind of scratching their heads because you've got this, first of all, there's not that many fossils. And what you do have, it's very hard to tell who's who. It's a sort of grab bag of features. They're sort of sturdy creatures. Some of them get quite large. By large, I mean, sort of cow size maybe. Things like Barrelambda get quite big, but they're very chunky and it's very hard to tell who's related to who and in what way. And that really hasn't been very well resolved yet. It's really not until a little bit later that we start to quite clearly see the earliest members of the sort of major mammal groups we know today. And most of those are defined, actually, they kind of have their origins in particular regions of the world. So things like the Afrotherians, which include elephants, hyraxes, manatees, they seem to have their origins in sort of northern Africa, Arabia sort of region, and have since, some of them have spread out from there. And Laurasiatherians, in Laurasia in the north. That's so, as I say, a little bit later, in sort of around 50 million years ago, that we really start to be able to say for certain who's who, and trace it from that point onwards.
Okay, and then I haven't written any more questions. I think because I ran out of interest post KPG.
Well, no, but you're quite right, because actually in the book, I stop at the KPG pretty much. Because there's been a lot of books about the origin of mammals, and they always start at the KPG, as if that's the origin point of everything, and it's not. I mean, that might be where we tend to think about, because we're quite selfish. We tend to think about the human line, and some of our earliest sort of primate ancestors appear around about that time. But I think there's been a lot of books that cover that time period. So I pretty much stop there, and then I jump ahead, and at the very end I kind of postulate what might happen to mammals in the future with climate change. Ooh. Yeah, I don't go too speculative zoology about it, but looking at trends in climate now because of climate change, human-induced climate change. What do we see from the past? What does what we see in the past inform what might happen in the future? So, for example, I talked about Lystrasaurus straight after the end Permian mass extinction. It was a sort of really stocky, probably competent burrowing generalist herbivore. So you might think something like that would survive really well through climate change. Things that basically are generalists, are flexible and adaptable. And of course, I talk about things like, with our climate getting warmer, you might start to see mammals become more nocturnal than they are now. I mean, a lot of them are nocturnal already, but that might become the sort of dominant time to be active for most mammals, because the daytime might just become too hot. You might start to see populations shift poleward or up mountains as they find the sort of plains too hot. Things like that. I speculate about it a lot at the end, but I mean, you can only speculate. And of course, hopefully, we can mitigate some of the impact of these things in the sort of coming decades.
So what can we do to eradicate this misconception of mammals being small, opportunistic asteroid dodgers?
I don't know if we should dispel it entirely. Because they were generally small. I think the problem is that we like our stories very simple and linear, and of course that's just not evolution, is it? This, when it comes to size, the synapsids have ballooned and shrunk multiple times in different lineages, and we've got this sort of messy network of one lineage shooting off, becoming extinct, another one here shooting off, becoming extinct, and we can't always trace who's who. So I don't think we should bin all of these misconceptions. I think we should just remind ourselves that there's always a lot more to the story than we think.
And those details could be read in
They certainly can. They can be read in Beasts Before Us, the untold story of mammal origins and evolution. And that's published by the lovely people at Bloomsbury Sigma.
Well, Elsa, it's been absolutely brilliant, and I really do recommend everyone get hold of the book. It is a great read, and thanks for coming on the show.
Thank you so much for having me.
Paleocast was brought to you by Dave Marshall and Liz Martin Silverstone, with contributions from Tom Fletcher, Vish Venkat, and Elsa Panciroli. Music was composed by Patrick Kendall Smith. Paleocast was made possible by funding from the Paleontological Society and the Paleontological Association, but the show now relies on funding from you, the listeners. So, if you've liked this episode, please consider donating, and thanks to everyone that's helped out so far. Please visit paleocast.com for the supplementary material to this episode and for our archive of past programs, and follow us across social media platforms to get all the latest news. Finally, if you enjoy our podcast, then please explore all of our video content on YouTube and follow our other projects, the Virtual Natural History Museum and the Paleocast Gaming Network.